we calculated the electric field in Cartesian coordinates and for any point x and y. Now what I'd like to do is set up a calculation in which we look at the limit that the distance of the point P is much greater than the distance between the characteristic distance between these two charges. And what we'll do is we'll make an expansion, and the leading order term is something that we'll call the electric dipole field associated with these charge configuration. But before we do that, we have to rewrite our expression for the electric field in a manner in which we can start to make these expansions. So the first thing we want to look at is these denominators, which we'll rewrite in the following way. We'll write r plus p cubed, which is equal to this quantity, which is the distance from the positive charge to p. And what I'm going to do is first expand that, x squared. Now when I expand y minus a squared, I get y squared minus 2ya plus a squared. And that's all to the 3/2 power. And I'm going to pull out the r squared in here. And when I pull out the r squared, we'll rewrite that in the following way. R squared minus 2ya plus a squared to the 3/2. 2ya, there's an a in there. And now when I pull out the r squared, this is a little bit complicated because you're taking an r squared out, something that's to the 3/2 power. So first you'll take the square root, r, and then cube it. And so we get that r plus p cubed is r cubed times 1 minus, well, let's do plus, minus the quantity 2ya plus a squared over r squared, all to the 3/2 power. Now, what I'd like to do is, this is a complicated term. I'd just like to indicate it as 1 plus s plus to the 3/2, where s plus is equal to minus 2ya plus a squared over r squared. Now, when I look at r minus p cubed, that's this denominator here, which is the distance from the minus charge to the plus charge. Everything is exactly the same, except when I do the square here, instead of having a plus charge, a minus sign here, I'll have a plus sign. So that will be plus, plus, and I'll call this s minus. So I'll write this as r cubed times 1 plus s minus to the 3/2. And the only difference in this calculation is that s minus is plus 2ya plus a squared all over r squared. And that's the first step in setting up our expansions. But now what I'd like to do is I'd like to write my electric field as it's a vector field, so it has an x component function and a y component function. And I'd like to treat each of these component functions separately and get expressions for them. So let's start with the x component function. What I'm doing is I'm taking this first term component, subtracting from that. We see both terms have our constant kq. In the denominators, both of them have an r cubed. In both numerators, there is an x. And the only difference is the denominator here is 1 over 1 plus s plus to the 3/2. And the other one is a minus, minus 1 over 1 plus s minus to the 3/2. And that's our x component. Now, the y component, it's very similar. We have the same kq over r cubed. What we have here, notice we have a y minus a minus y plus a, and the denominators will be similar to those expressions. So we have y minus a over 1 plus s plus to the 3/2, negative, because the other charge is negative, y plus a over 1 plus s minus to the 3/2. And this is, again, another way of rewriting this expression for the electric field in terms of its two component functions. But now that I have it set up in this way, I can now make a power series expansion of each of these quantities using the Taylor formula. And that's where we'll go next.